Hi everyone, and thank you for joining this broadcast. And thank you also to the primary sponsor of this broadcast, which is Women in Engineering for IEEE, and also the special broadcast for today, the IEEE Engineering in Medicine Biology Society. I'm delighted to have this opportunity to share with you the journey that I've undergone over the last few decades in now specialising in health informatics. So during this broadcast today, I'm going to be telling you a little bit more about myself, the journey that I've undergone to learn about computing and engineering, and my ultimate work now to help premature babies. I'm going to tell you about the roles that I have in IEEE and also about my research work. So my name, as I said, is Carolyn McGregor, and I am the Canada Research Chair in Health Informatics, and I'm based at the University of Ontario Institute of Technology, which is in Durham region, on the outskirts of the GTA in Ontario, so the outskirts of Toronto. And within IEEE, my role is that I'm currently the Canadian representative for the Engineering in Medicine Biology Society, and for that society I'm the representative on the Women in Engineering International Committee. So I'm working with both groups to promote women in engineering and Engineering Medicine Biology Society within and outside of IEEE. I go and I give a number of invited talks, much like I'm doing today, but I also try and help new chapters within Engineering Medicine Biology to start, and also work with various women in engineering groups in IEEE, and also provide support for high school students, girls and boys, trying to understand a little bit about their careers. If you have any questions today, please do put them in, and I will try and answer as many of them as I can while I give my presentation. When I was in high school, albeit a little while ago now, I was very interested in mathematics. I found also logic problems very interesting. Some of you may have seen the logic problem grids where you're given a paragraph of information and you have to match up all of the details of what person had what surname, had what pet, had what interest, what favourite food, etc. And I always had a fascination with those. And I also really liked mathematics. When I left high school, I had a choice of whether to join sort of industrial mathematics through operations research or to go on and do computer science. The one piece that really governed my initial journey into this area was that I saw a cadetship in computer science advertised, and I took that cadetship. It was offered to me, and I ended up studying in computer science. So I spent the first several years of my working career working for a bank. That was a very good grounding in production systems required to support a real business need. And I was very fortunate when I was working in that setting that there was a brand new type of computing that was started. The managing director of the bank I was working for in Australia at the time saw somebody else, a counterpart of his in Europe, who had this new computing system that could tell him about the operations of his business. And he wanted one of those. And as a new computing graduate, I was very fortunate at the time to be asked to work on that project. That was one of the very first analytics projects as they're known today in Australia. I ultimately went on to lead that project. I was actually headhunted by the largest retail chain in Australia to do the same thing for that company. So I found myself specialising in this area of analytics. So my first piece of advice is that it really helps if you specialise. Keep your skill current in an area, but you really should think about how you can specialise. And so I was starting to specialise then what was called executive information systems and data warehousing, what now gets called analytics and working with big data. And so from there I spent several years then working for these organisations, helping build these analytics systems. And I ultimately decided to extend that specialisation and become a consultant. And so back in the late 1990s, that's the type of work that I was doing. From there, I went on and was doing some PhD study because I found that there were areas I kept seeing as problem areas when we tried to implement these systems. And I went to start my PhD, and when I was re-engaged with the university, I met a neonatologist who had come to the university and really wanted to do more with the data that they have at the bedside. And ironically, when I met him in 1999, I was pregnant with my first child. Sadly, she was born with a very rare chromosome abnormality and she passed away. And I was very sick in that process. One of the interesting things that I went through at that time was that it was literally, I was very fortunate that that particular day that everything happened was a day that I was due to see my obstetrician, or OB/GYN as some of you may know them. But there were things that were changing in my body that I wasn't really aware of, that if I was wearing a monitoring system, somebody could have realised the catastrophic events that were occurring for me. And my blood pressure was well over 150, my heart rate was accelerating, but eclampsia and pre-eclampsia are actually referring to what's known in the Greek as lightning, because for many in the medical industry these things come on suddenly. So that was really an introduction for me personally to the need for physiological monitoring, but also professionally I'd started to work with a neonatologist. So I'm going to spend a few minutes now just taking you into the world of neonatology. And as you'll start to understand, you can really start to help and support this whole area of medicine by doing far more than just becoming a nurse or a doctor, which are very important and vital roles, but we need so much more. And so you'll start to see how careers in health informatics and in biomedical engineering really have the great potential to help people, but have the ability, rather than that one-on-one connection, but to go 1 to 1,000 by providing strategic solutions. So in my case, we go into now the world of neonatology. Babies are normally born after anywhere from 37 to 40 weeks of a gestational cycle. If they're born before then, their lungs have the potential to not be fully developed. The further earlier that you go, more of the organs are not developed. It's not just that they're smaller. In most countries, a baby is considered to be viable once you get up to 23 weeks gestation to be able to survive and have the potential for a good outcome if they are that 17 weeks early. So that's 4 months early. So there are specialist areas in hospitals that are designed to take care of these very small babies. They weigh as little as 450 grams or a pound if you're used to that in weight. The head and the body of these babies, when they're very young, can fit in the hand of an adult male. They are very small, they're very fragile, and they're still developing, and they need to be supported. So many times a mother and a partner will be looking forward to the birth of this child, and they're thrown into this world where their child has been born earlier than they expected. Sometimes it needs to be transported to another location where they can provide this intensive care depending on where you live, and they themselves need to recover from the birth, and the child needs to now be supported. So when you think about what you use in social networking, what I'm doing today, where you can hear me speaking and you're watching what I'm discussing with you, let's think about what it's like, for example, in a rural or remote area of Australia or of Canada, as an example, because those two countries have large geographic areas that are sparsely populated. And if you happen to go into labour early in that area, then a local paediatrician or an obstetrician will give a call to a referral centre that can support caring for that child, and they will start having just a telephone conversation about the fact the baby's going to be born. and any complications that may already be evident. And so in those situations, the baby then is starting to be cared for by that neonatologist, but all they have is a telephone conversation. And so the mother goes through the birthing process, the baby is born. Some instances they need to then start helping the baby to breathe, and they need to arrange for a transport team to go and get that baby. Now all the while, in terms of being supported by technology, the neonatologist is listening in on a telephone, sometimes for hours and hours, talking them through, trying to understand what information is showing up on the medical monitor for the heart rate or for their breathing or how much oxygen's in their blood, trying to understand what they need to do to provide support until that specialised team can get there. In some of the very remote and rural areas of larger countries, transport has to happen by either an aeroplane or a helicopter. And currently, when that transport team is in the air, it's what's known as a blackout. There's no information. So if something happens and they have to resuscitate that baby or any other complication, in very, very rare instances, they can use air traffic control communications to get a message through to the hospital. But it's usually a blackout until you land. Now, when you think about flying now on an aeroplane, some flights in North America do provide you with internet access when you're flying, but usually we don't have that yet. And the same happens when you have medical transport. So if there is a long flight that can take a couple of hours, you're really not sure what the patient's going to be like when they come in. So these are some of the challenges. And then it could be that the baby's born within the hospital that has its own neonatal unit and you're just transporting them straight into that ward. When they arrive, they're connected up, depending on their age, they'll have their heart rate and respiration rate monitored and blood oxygen monitored. They may have a tube put down into their throat to help them breathe. And a whole lot of numbers start flashing on the screen. They'll take you into an intensive care unit. You can hear the beep, beep, beep of the heartbeat. You can hear certain alarms going bing, and you can hear so much activity from all the different medical devices. And a lot of people think that it is quite a complex and futuristic environment for them to work in. But the reality is that a lot of what they do is still paper-based. And if it's not paper-based, the information is the same sort of information, but now available on a screen. So let's think about an example. These very tiny babies are very susceptible to becoming infected, whether or not it's from where they put a line in under their skin to be able to have direct access to the bloodstream, or whether it's the tube that's running down in through their throat and down into their lungs to help them breathe. Sometimes bacteria can grow and they start to get infected. Now currently, if they are trying to detect when a baby's becoming infected, it's usually when they have a lot of issues occurring from that infection in their body, that they really start to show that they're becoming unwell. So we have computing tools and we have these biomedical engineering devices that people have built to be able to use leads on the chest to be able to show diagrammatically the beating of the heart, and it can then derive a heart rate. So they can see changes in the heart rate, but they really don't have tools to say that something's happening in the body. What some recent research has shown is that if you actually sit and you watch that heart rate, then you can derive from that subtle changes that the heart is becoming under pressure and the nervous system is coming under pressure, potentially from infection. So as you're listening to me give this presentation to you now, you're probably sitting comfortably back, maybe with a cup of tea or coffee, and you're sitting relaxed. The fact that I'm drawing your attention to it now might make your heart go a little bit faster, but you may think that as you live your life that your heart is beating quite steadily. In actual fact, it's not. Two parts of your nervous system constantly compete with each other to try and regulate your heart. And that is your the fight and flight reaction when you get a shock, and a calming influence when you're just sitting and being nice and calm. And what we've started to find, if we look at every single beat and every single breath, then we can start to see when that nervous system reaction to change your heart is being impacted. And it turns out that that's the type of indicator we can use that will tell us that your body is starting to come under stress of something like infection. So they're the sorts of things we're learning about. And let's go back to the idea in a neonatal unit of the way they work today. They have a lot of medical devices that flash up those raw heart rate numbers on the screen. A baby's heart beats on average around 120 beats a minute for a premature baby. It gets closer up to 140 or even 160 when they're awake, if they're upset, and all different reasons. So it can be quite fast. That's over 7,000 times an hour the baby's heart has been beating. They breathe more than 2,000 times an hour, and more than 3,600 times in an hour we check their blood oxygen levels. Now, in some countries, in some hospitals, every hour, one number is recorded as an indicative, as a best guess of an average really of what the heart rate was in that hour, one number for the respiration rate, and one number for the blood oxygen level, just those three readings. And that's recorded on a chart to represent the baby's state. And then in the next hour, if the baby seems quite stable, then they can write the same sort of numbers down. In some hospitals, they record those numbers electronically every hour. So in the last 15 to 20 years, we've been able to make changes so that we can either automatically derive a summary, or we can just have nursing staff put a summary into an electronic chart, but we still have an enormous amount of reduction of the data that you have available when it goes into a chart. So 7,000 beats a minute, an hour, to one number on a paper chart. So you can start to see that there is enormous potential. In some research, they've found that up to 24 hours before the current way that they suspect infection occurs, you start to see these changes in the heart rate. And in our research within the system that we've built, we can see potentially changes in heart rate and respiration rate at the same distance. And it's important to have these multiple streams because there's different reasons that heart rate can change. So we're working on new systems that can be used not just in neonatal intensive care, but in intensive care broadly, that can detect when any patient is becoming unwell with infection. But we need to introduce a whole new set of computing systems that can extract from the sensor that is acquiring that heartbeat and automatically in real time process data at a very high speed. In our research, we're processing usually 1,259 data points per second per patient. Because when you look at that nice traditional graph that you see on a screen of the heart beating, if you've ever been in an intensive care unit and watched that beating sign, it takes 1,000 points a second to construct that. So we're using that information together with other information about the patient. It's important for us to know their gender because the resting heart rate of males and females, even at this early age, is different across the board. We need to know their gestational age, how old they are, helps us to understand the range that is acceptable for where their heart should be beating, what sort of organ development we should be expecting. So it becomes quite a complex problem. And so we're pursuing this work with the Hospital for Sick Children here in Toronto, and also with the Children's Hospital of Fudan University in Shanghai, Women and Infants Hospital in Providence, Rhode Island, and we also have partnerships in Australia and in Ireland. So this really is what's known as a big data problem. We have a large volume of data we're trying to process in real time, and the data itself can't be assumed to be very similar from second to second. So one of the ways that people describe this area known as big data is they talk about volume, they talk about velocity, and they talk about variability. So the volume, when I was telling you about the number of readings that you have every second, it's quite a significant volume. The fact that the velocity is the speed that it's coming in at every second, and the variability, because you can't assume that because a heart rate has a certain value in 1 second that it's going to have another value in the second, because there's a lot of things that can happen. So that's what makes this what's known as a big data problem. So in this context, we're looking at a number of medical conditions. So although my training is fundamentally in computer science, and what can also be called in some aspects computer engineering, my specialty areas are with databases, with data mining, and particularly temporal data mining. Some of you may also have heard terminology such as cloud computing, so you can provide computing support remotely. It's another one of my specialty areas. So we're using these techniques in neonatal intensive care to address very real problems. Infection is a problem with very premature babies and all babies in the neonatal intensive care unit. Approximately a quarter of babies who are very premature will get some form of infection, and 10% of those will die. So that is why this is a very important problem for us to work to address. In our research where we are at the moment, we have built the system. It has been collecting information in real time in parallel with the way that the doctors currently work, so that we can compare when we start to see the changes in the babies and when they start to see something at the bedside, or the nurses start to see something at the bedside that makes them suspect there's a problem. There's other conditions we can help with as well. Very premature babies forget to breathe. Their nervous system is not developed enough that they can have that automatic remembrance that they need to take a breath. And sometimes the fact that they pause in breathing or their heart rate slows down is because something else is happening. At the moment, nursing staff at many places around the world will tell a doctor the baby's having spells, as in the word magical spells. But spells broadly means the change in either heart rate or breathing or blood oxygen. But they don't have the mechanisms to easily tell the doctor how long that pause was, how severe that pause was. They try their best to keep track of how many have occurred. Sometimes if they almost reach the threshold and they don't, the alarm won't go off. So they really, again, don't have the right tools. So that's another thing that we're helping with. We are working on new computing algorithms or automating what they're looking for so that they can detect these things in real time. Something else that can happen with these babies is that they can get too much oxygen, which sounds strange, but inside the mother's tummy as they're growing, they don't get as much oxygen as you and I are breathing when we're born into the world. And it turns out that there's a lot of research that shows if they get too much oxygen, they can actually go blind. Some of you will know of a musical artist whose name is Stevie Wonder. Stevie Wonder is blind and is in his 60s, and he was born premature. And the reason that he is blind is that his developing eyes were damaged, what is now believed to be due to too much oxygen. He was born at a time where the Western countries just started introducing oxygen therapy to help the premature babies. And it's had some really great positive outcomes when you provide that supporting oxygen to the baby. But now they've been learning that the level of oxygen is important, and keeping oxygen in certain ranges is important to prevent brain damage and to prevent damage to the developing eye. So you have to have it right in that range that it needs to be. And they need better tools to be able to watch these things. There's a whole lot of examples in neonatal intensive care, but it goes beyond that. There are things we can watch for in adult care, but also with people in their homes. Now, I'm not saying they have to be wired and connected so that they can't do their things in their homes, but it is helpful for people who are dealing with cancer, people with chronic conditions, that there's some sort of continual monitoring in the home. And so the platform that we've built will support that. Because I'm a computer scientist, and the same thing applies for engineers, we are all working in the same space in computing, we need to build platforms, infrastructures, to support the way people work. When I started looking into this area, one of the things I did was to understand how people were performing research in the area. And one of the things that they're doing for their research was to take a laptop or some other computer, wheel it up by the bedside, manually connect onto a medical device, capture the information for that patient, and move on to the next person. And you'll see that if we're trying to build whole new systems, that's not the way you can work. You need to have infrastructures that are collecting the data from all the sensors for all of your patients and provide a platform to connect to all patients, to watch for lots of conditions, to connect to lots of different medical devices, ultimately integrate sound and video. There's been some research in the neonatal space that cry signature behaviour correlates with those babies who have died from SIDS, or sudden infant death syndrome, which is largely it's not understood, and that parents will wake up in the morning and unfortunately their baby has passed away in the home. It's still a condition that's not very well understood. So, and also video, watching for certain things on a video. There's all sorts of research that's happening in these areas. But what I'm interested in as a computer scientist, and why it's very important for women and men to train in computing, is because we need to broadly understand the working practice needs of people in all different areas, and I'm focusing on health to help with people and patient outcome. We need to understand the way they're trying to work and to make it better. We have to not introduce computing systems that make it harder for people to work, so we really have to understand their working behaviour and to try and make it better. So when I give talks now about this type of area and the work that I'm doing, people actually often think I'm a medical doctor. They think that I'm a specialist for these preterm babies, which are called neonatologists. And I take that as a compliment, because I have worked really hard to try and understand as much as I can about the domain, about what I'm doing, so that I can make sure I provide the best solutions possible for the doctors, the nursing staff, and all of the different roles that they have within this environment. So there's a lot that we can do even if we don't train to be a medical healthcare worker. If fundamentally your interest is in solving problems, solving logic problems, if you like working with mathematics, we do a lot of work with statistics as well when we try and look back over patient information and try and find common trends and patterns. And it's very rewarding. The computing and neonatology isn't all my world. It's something I'm very passionate about. It's something that I want to change. I want to help more babies to survive, and I want to help the families. But it's not all of who I am. So in the time that I've developed and learnt more about computing in the time we've tried to grow these research projects, such as Artemis, I got married. As you've heard already, my husband and I lost one child. We've gone on, fortunately, to have other children. So my working life is busy. I have learnt along the way the good and the bad of what works in terms of balancing work and life. I was very fortunate in terms of when I was initially pregnant with my first child, working as a consultant, I had felt that I would be able to balance and take a step back from consulting while I wanted to have that first year with my child. As it turned out, I needed a few months from a health perspective as well as from a mental health perspective, recovering from all that had happened there. But ultimately I ended up pursuing a career in academia after I completed my PhD, because it seemed to be a good environment to support a work-life balance for myself. It was good to be able to step back and when I was able to have my other children and take maternity leave. But in a researching context, I still found that I needed my adult time. I wanted to be able to read and understand what other people were doing in research, think about what else I was doing in research. But one of the things that I really learnt was very important when you're trying to do that, when you're caring for a very small child, is to try wherever possible not to have time constraints, those hard deadlines, because it would always happen that when you had a hard deadline coming up, that was when guaranteed the child would be cutting teeth, unwell, keeping you awake all through the night, and you would sit the next day when they were sleeping in front of a computer and, I don't really feel like working today because I don't think I can do this. But setting yourself up, if you're the type of person who wants to have that mental stimulation, still looking into areas, there's lots of opportunities that you can pursue while you have children and you're still caring for them at a very young age. My children now are older, they are both in school, so my routine is very busy. My students understand my working dynamic, as do a lot of people who work with me, that usually one of my children will wake, if I'm not already awake, one of my children will come in and say good morning in the very early hours of the morning. And I may have a chance to quickly check what emails have come in overnight because I know people in different time zones all around the world. But my morning, first couple of hours, is very much focused on my children, making sure they have lunches for the day, making sure homework's gone back into bags, doing any last minute work with them on something they may need to do that morning for school, taking that moment in time. It's important for me whenever I can to be at the school gate, to take them in, to be there, to have that experience with them. And then coming to the university or to go back home around 9 o'clock and essentially switch hats and then start my academic work or my research work, and then continue on with that until it's time for either myself or my husband to pick my children up from school. Wherever possible, I'm trying to be there for my children. We only get one shot of this in the windows of time where they are this age, where they're needing this type of support. So it's always been really important for me to do that and to be there for them. So then in the afternoons, again, I've switched my hat back to my mum hat and my wife hat, and I'm there and I'm helping my children with homework. We've had years and years of me reading to the children, them reading to me, which has been a very special time, particularly when they're going off to bed. But initially in the afternoon, homework and riding bikes on a trampoline, all sorts of things with them. And making dinner, I do enjoy cooking. For the most part, I find it very therapeutic and peaceful to cook. And then getting my children ready for bed, having that reading time with them. And most people know that with the children that the age that they are, that usually by about 8 o'clock in the evening, I can start having my time again, which rather than just sitting watching television, I'm very interested in having the time back for myself, and usually that means getting back and doing my research work. I find the evening hours for me as a working pattern very handy. I can sit uninterrupted in the evening and I can work on through new concepts, I can write research papers. But it's really about when you have a family, whether you're the father or the mother, finding that working pattern that works for you. Having that time with your children is very important for them. It's a wonderful experience for yourself. And it's possible to do no matter which company you're working for. If you have those discussions with your employer, if it's not as an automatic, flexible environment as, say, a university is, you can think about how you can restructure your workday, show that you can make those measurables and deliverables, and get that environment to work for you. It doesn't always work, but it's something that I'm trying to do, and I try and work towards every day. So that's a little bit about how I work. Just switching back now to from the computing perspective, I've touched on it a little bit briefly. You understand about the fact that I'm working in a big data problem. I'm working in this biomedical space for computing and engineering and health informatics. So we've built a computing system. It's called Artemis. Unusually for people, if you work in computing, you know that we often come up with lots and lots of acronyms, which they're taking the first letter from each word and coming up with a name. But Artemis is actually named after the Greek goddess of childbearing, which we thought was quite an appropriate name for the system that we're trying to build to oversee all of these babies in a computing sense, as opposed to in a Greek mythology sense. And so the environment, I'm going to go into some of the technical detail for those of you who are a little more technical and are interested in the technical details. My background is, as I said, in computing and data warehousing, but also in event stream processing. So we're using a different concept of event stream processing called stream computing. And in stream computing, we understand that as the data is arriving for us, it's inherently in a stream. And when you think about sensors like heart rate and respiration rate, they are continually polling and sending you potentially that information, and it comes in a stream. So I was very fortunate when I moved to Canada that I met some researchers from IBM at a conference I was presenting at in Toronto. And at the time, I was presenting this early work that we had done to capture these signals and try and cross-correlate them, try and understand their behaviours and do it all in real time. And that a lot of my work had been spent and my time had been spent building an engine that could do that type of work. And we still had a lot to do. It was very early work of that engine. And I was very fortunate that some researchers from the IBM TJ Watson Research Centre in New York came to me and said, look, we have an engine like that. It can process streams, but we haven't processed streams in healthcare at the speed that you have. So I was very fortunate to be awarded an IBM First of a Kind Research Award. It's a multi-million-dollar award where IBM dedicates people and computing to try and solve a new problem. And so if you Google IBM First of a Kind, you'll see the project. There's also a lot more information about our research at our website at hir.uoit.ca. So healthinformaticsresearch.uoit.ca. So we developed this collaboration where we were looking at trying to apply stream computing into healthcare for the very first time. We built the environment that took that base stream computing and added a layer on top to start to understand physiology, start to be able to process patient information. And then we entered into, I joined two different collaborations that I had, one where I'd been working with the Hospital for Sick Children and a neonatologist there, Dr. Andrew James, and also then working with IBM to build a platform. The platform to allow multiple streams, multiple patients, multiple conditions, do it in real time, to be able to capture that data, to be able to use it for data mining. We needed to build that infrastructure. So that was the infrastructure that we've now used for the implementations at the hospitals, and it's known, as I said, as Artemis. We have Artemis Cloud, which is the cloud-based infrastructure so that hospitals can just connect their medical devices through a network, allow us to connect to that, as well as some information from electronic health records, and gather that information as well and bring it all together in real time. I've been very fortunate to progress our collaboration with both institutions. In particular, very excited that IBM has established the IBM Canada Research and Development Centre here, and a collaboration with a couple of the universities in Ontario, and we have a flagship project as part of that collaboration where we've been able to demonstrate that these types of systems are possible. So now we're working on the next stage infrastructure in a cloud so that any hospital in Ontario can join, can be providing their data in real time, and we can have our standardized algorithms for infection, for detecting blindness, to detect spells, and to be giving them that information back in real time. We're also working on that cloud infrastructure ultimately with what we're doing in China as well. And then we're literally looking logistically about how we're going to connect up multiple nodes. So that's why I now have computing expertise in cloud computing, stream computing, event-based programming, and data stream, data mining, and a lot of other related areas as well. One of the other things that I do is when we watch the way people work, we try and monitor their behaviours. So we try and draw diagrams about the care of a patient, what activities take place, who's involved, what steps, what information they use, what's on paper, what's in technology, and that's called patient journey modelling. So we're doing work in that area as well. It's very important in these projects that you bring together people with all different skill sets. So in my research team, we are working with the neonatologists, we're working with the nursing staff in this context, with the respiratory therapists as they had in North America, who help to support breathing and control the ventilator settings. We're working with a whole lot of different specialties. In my research team at the university, as the leads on the research, we have a computing and software engineer, myself in computer science and health informatics, biomedical engineering. We have people who are operations research, we have the neonatologists, and for our students we have computer engineering students and biomedical engineering students, health informatics students, computer science students. We have people who are trained in neonatology who are completing their masters in health informatics, the same as those trained to be critical care nurses, obstetricians, paediatricians, and we have people we're training who are based in Australia, who are based in Canada, and who are based in China as well. So it really is quite a broad team. We work in a very flexible working environment. I communicate with my team regularly in the laboratory. We speak on Skype late in the evenings for those of us with children when they've gone to bed. We use a range of different communication technologies to stay connected. We share Dropbox folders. We use a lot of tools so that I can be attending a conference in China, in Europe, anywhere in the world, and I can still be connected while I'm awake with my family, with my team. I recur in terms of staying connected with my family. When I go away, something that technology has really helped me with in varying forms over time. I used to speak to my children through Skype. I would take the books that I'm reading to them with me initially. I would read to them wherever I could, where the time zone allowed, that at the time that they were going to bed, that I could read to them. Sometimes through Skype, those connections didn't work that well. Now I can record voice memos. So I take photographs of a couple of pages that I'm up to in the book that I'm reading, enjoying going through Harry Potter and Zach Powell, Harry Potter with my daughter, Zach Powell with my son. And so I record those things. I speak to them on Skype wherever possible. I say good morning to them when they're going off to school, getting organised. I help them with their homework. All these things really are possible when you can use technology and you have a supportive spouse and a supportive family around you to be able to stay connected. My family, my husband and my children moved to Canada when my children were very young. So my children stay connected with all of our family back in Australia using video conferencing tools like Skype or other tools as well. So making these things work, and it doesn't work every day. Sometimes things don't come together as well as we would like in our lives. But taking that conscious effort to realise you really can be in control of how you interact every day, what you're doing in every moment in every day, who you're engaging with, how much quality time you have with people. All these things you really can take into control for yourself. So these are some of the lessons that I try to bring through now in my roles with IEEE, whether it be to try and bring my messages about health informatics and biomedical engineering through outlets such as the Engineering, Medicine and Biology Society. We're trying to create that collective group of people who have interest in similar areas that can use computing tools to communicate, to mentor. We have a great new program in EMB that's a new mentorship program So if you're interested in, or you're in Engineering, Medicine, Biology Society, I encourage you to do that. We have programs like that for women in engineering. We are really trying to change the face for elementary or primary school boys and girls, and high schools for girls to understand that engineering and computing is a great career choice. To create those support mechanisms at university for, particularly for the young women. When I was studying my computing degree, I could count on one hand probably the number of girls who were in my class of 200 students when I started. So it's important that, that the girls and boys feel well supported through their graduate studies, and there's lots of wonderful initiatives that we're starting through Women in Engineering and EMB. We can't do all these things on my own. Just the same way that in my research with Artemis, I really can't do it on my own. I need people to step forward and to volunteer and to also come into these discipline areas. There are so many opportunities for you to volunteer with Women in Engineering, with the Engineering and Medicine Biology Society, in your local community, more broadly, working on initiatives to take the messages we're developing to your local schools and to bring those messages home. There may be projects that you can get involved with in your local community to support in healthcare if you're wanting to start getting involved. And for those of you who may be more senior in your years, who are looking at retirement, this may be something that you can think about in terms of volunteering. I have a question that's come in. So the question is, what is your most gratifying career achievement? That's an interesting one to think about. I've had a couple. First of all, in my working career with the banking and retail environment, that very first time when you give the system to the executives and they can see a behaviour that they were completely unaware of, and something very detailed and specific to do with a particular store or a particular branch of a bank, that they can then go away and action straight away. It was very gratifying to me that I've helped somebody solve a problem. And while we're not yet at the point with healthcare where we are changing care at the bedside for an individual baby, I know it's coming. And the very first time when we used my new computing technique to look for new behaviours, and we found some, and on we found that this behaviour with looking at heart rate and respiration rate variability has the potential to give them a tool that helps, is very gratifying. So if you have any other questions to come in now, I can take any other questions that you have, whether it be from a computing perspective about my research, about family life balance, about leadership. I'd be very happy to take your questions. And if there's anything to do with what type of characteristics you want to, you need to develop. If you're in high school, it's very good for you to, if you like mathematics, to stay with mathematics and build up a very strong skill set in mathematics if you want to move into the biomedical engineering domain. Also, I didn't take biology in high school, and here I am in an environment where it probably would have been more helpful, but it's one of those things that I was still able to pick up skills along the way. And I think that's another important message, that you have a base set of skills that you learn through high school, but there are all sorts of ways that with determination and good grades that you can switch and move into an area that you're very interested in. So I have another question that's come in. Has anyone ever discouraged you from becoming an engineer? I must share with you something from my father. And it came through, and he knows that this is something that I now talk about. I was in grade 8 or year 8 in high school. It was the first year where they had ranked everyone in the year in mathematics in their performance, and I'd come first. And I came home and I told my parents that I'd come first in mathematics. And my father sat me down for what's now famously known as the plateau speech, as in a flat area, a plateau. He said to me that it was wonderful that I seemed to be understanding the concepts of maths at this point in my life, but there were probably going to be a lot of other people who were going to ultimately become much smarter than me. That it probably wasn't really something that I would be able to continue and pursue. That my ability to understand things would probably get to a point where it would plateau out, and that other people would surpass me. And I have to say that I was absolutely stunned. And as a child, I was really surprised and annoyed. So it turns out that that's probably one of the most important things that happened in my life, because I was so annoyed and so determined that, and really interested in mathematics. So I then went on to top the year in Year 9 and Year 10. I came second in Year 11, and I then topped the year again in Year 12. And in my university studies, I graduated second in my year. And in my PhD thesis, in the acknowledgement section, I acknowledged my father, and I acknowledged the fact of that plateau speech and the impact that it has had on my life. My father now recognises, he doesn't know whether it was a good or a bad thing now that he's done it. I think ultimately it's been good. And I recognise that I'm not going to plateau, that it's not in my late nature. I continue to be interested. Other people along the way have come along and said that it's maybe not the best thing for me, but there are so many examples and so many people you can get support from if it's really what you want to go into. So I hope that that's answered your question about people discouraging you, because there are people who think that what's known as the STEM disciplines, the science, technology, engineering, medicine, careers for women, when they really are. Because we think about the impact on people, and we think about how people work with people. And broadly, and it's just that research suggests that women tend to think more about that than men. So I have another question that's come in. How does the principles of science and mathematics apply to your everyday tasks? Well, this I find funny because I'm now helping my children with maths, and I look at what they're learning and what I use today. So we use a lot of different mathematics tools and techniques in the analysis work that we're doing every day. So trying to look at new ways to analyse the changes that we have in heart rate. We can do things like frequency histograms on an hourly basis and look at what sort of range we have in a given hour for the heart rate. We can do various statistical distributions. We use different differential equations when we're looking at the impact of drugs on the body, which is some of the work that we're starting to do now, modelling virtually the impact that a drug will have in the body. As I mentioned before, I didn't study biology, I didn't specialise in it. I did it in the early high school years, but not the later years. I think ultimately there's a lot of things that I wouldn't have had to learn at an older age that I could have learned at a younger age if I'd have learned, if I'd have studied biology. There's other areas of science to do with logic and reasoning and other scientific systems that are beneficial every day. So if you're in high school and you have the interest, then certainly, you know, the physics type subjects, biology, mathematics, they are the ones that I was studying. Interestingly also, I studied economics. So now when I need to look at, when I was working within the bank and I was having to do profit and loss statements and balance sheets, I've run my own business, I needed to understand those things. That's been very important for me as well. Understanding the cost-benefit models for new treatment practices, that again is something that we need to look at if we're going to convince hospitals to do these things. I have another question that's come in. Who was my role model when I was young? Interesting question. And I can't say through high school that I really had a role model. I was really struggling through working independently and realising that I was interested in something. I know that in high school there was a particular maths teacher who really made maths real. In anything we were doing, we would go outside, measure trees by using protractors and measuring angles and all sorts of things where we could really understand the realities of why we needed this mathematics. In my adult life, one of the lecturers who was a female at where I studied, the University of Technology in Sydney, Professor Jenny Edwards. She was a lecturer when I was there. She was ultimately my PhD supervisor. I learnt so much from her about the discipline of computer science, supervising students so they can complete on time, and learn so much about mentorship. And I learnt so much about her from being a female in this area. She was really one of the great role models for me when I was an adult. So that's the answer to that question. I'm not sure if there are any other final questions for me today. There are lots of ways that you can reach out to me depending on what you're interested in doing. We need help. We need people to be more volunteers in Women in Engineering. We need more people to step forward for the Engineering and Medicine Biology Society to bring these messages to the high school students, to be mentors, and to help us to connect as a community. One of the things that's different from when I was growing up, we really need to now be that connected community, and we can. People who are working together towards a common good. There's a real growth in the philanthropic ethos around, or wanting to work for the common good, do things as a volunteer. That's something that I really feel over the last couple of decades has grown more and more. There's a change in work practices. People don't just always want to work the long hours. They want to be there at the school. They want to be there volunteering and helping others. And so I would encourage everyone to try and be involved. So you can connect through the Women in Engineering website, through the Facebook page. Engineering and Medicine Biology Society also has its own Facebook presence, so please look us up. There's an interesting article that we've made reference to recently on that website about the fact that LEGO now for the first time has introduced a female scientist as part of its LEGO minifigure series. So if you have children or you're aware of the packs that come, sort of the surprise packs of the minifigures, there is the chance to get the female scientist for the first time. I was only joking with someone this morning that now we need to look at how to get the female computing or the female biomedical engineer in there as well. So there's great information on the Facebook page for both Women in Engineering and Engineering Medicine Biology. We also have the websites for both. There's information about how to join IEEE on IEEE's website. There's information on the EMB website about how to join a great new and exciting mentorship program, some of the conferences we have coming up as well. So I'll look for any final questions now as we wrap it up. I want to thank again to both the IEEE's Women in Engineering Society for coming up with this great series. I want to thank the co-sponsorship today from the Engineering and Medicine Biology Society, which, as you've now heard, I'm heavily involved. And I want to thank you for taking this hour out of your time to listen to me, to listen to some of the messages that I can bring forward. So I don't think we have any final questions. So thank you very much and have a great day.